Well, first of all, thanks for watching this presentation. My name is Andrés Rojano from the Universidad de Concepción in Chile, and I will be talking to you about the electrokinetic transport of multivalent electrolytes, the effect of charge inversion. Miniaturized devices integrated by nanoconduits hold great potential due to their remarkable properties for biotechnical and medical applications. In these nanoconduits, the surface-to-volume ratio drastically increases, further modifying the behavior in the system in such ways that are not perceived at other scales. Here we can find the effect of wettability, which can be measured by the wetting contact angle. This exposes about the strength of the solid-liquid interactions. In the figure on the left, we can see in how the decay of the strength of solid-liquid interactions impose different boundary conditions in the system, which can be characterized by the concept of slip length. Here we can find negative, positive, and even infinitive values of the slip length. Acknowledging this, it is possible to understand why there are found some discrepancies in between the fluid dynamic theories and the measured variables from nanofluidic experiments. These discrepancies enhance as the fluid is a multi-component system, such as an aqueous electrolyte solution, given the electrokinetic phenomena that are found in them. Here we can see the model of the electrical double layer with the respective stern, diffuse layer, and hydrated counter and co-ions. In the figure on the right, we see the net concentration of ions in the proximity of this surface. As we see, the concentration of counter ions is maximum and the concentration of co-ions is minimum right next to the charged surface. And as we go further from this surface, these concentrations tend to equilibrate with one another until they reach bulk concentration where electron neutrality is achieved. Nevertheless, there are some cases in which the nominal charge produced by the co-ions exceeds the one of the counter ions in some region of the electrical double layer, thus leading to a macromolecule whose effective nominal charge is not reversed. This is known as charge inversion, and with this study we aim to shed some light about how these phenomena affect the hydrodynamic behavior of a nanoconfined aqueous electrolyte solution. To systematically study this, we employ large-scale molecular dynamic simulations in which we use periodic boundary conditions in all directions. We use the SPCE water model to describe the water molecule, given its appropriate reproducibility of transfer properties such as viscosity and diffusivity. The substrate in this study consists of amorphous silica slides described by the forcefully developed by Gucciani and Gilad. The silica-water interactions were described by Coulomb for electrostatics and Buckingham for van der Waals. It is valid to say that this force was calibrated in order to reproduce a water contact angle of 20 degrees. The ions in the solution were considered to be completely diluted, and their respective forfields were chosen given their appropriate description of the hydration shell, as this was considered to play a key role in the development of charge inversions. And all the simulations were carried out on the molecular simulation package lamps. Here we can see a description of the nanochannel model used in this study. As it can be seen, two parallel amorphous silica slides were separated between one another at a distance of 4.6 nanometer. In between them, some electrolyte of an ionic concentration of 0.4 molar was contained. Previous studies have determined that a type of this ionic concentration gives a surface, the one alike used in this study, a surface charge density of minus 0.9 electrical fundamental charge per square nanometer. We employ the Bernstein thermostat in order to maintain a constant temperature in the solution of 300 Kelvin, and specifically for the simulation where flow was being developed, the thermostat was applied only along the transversal direction to the flow. We use time step of 1 femtosecond for the vaporization process simulation and 2 femtoseconds for the rest. In this study, we conducted different types of equilibrium and non-equilibrium molecular dynamic simulation. Here we can also see the length of the simulation box and the share and type of the ionic species that were contained for the different cases throughout the study. Here I would like to talk to you about the equilibrium molecular dynamics simulations that were carried out. In them, the water and ionic species were within the NBATN sample enough time to ensure proper equilibration. With this simulation, we construct different charge profile across the channel for the different cases. We also computed the diffusivity using the Einstein approach, in which the mean square displacement is related to a function of time. As well, we also computed the friction coefficient using the following relation, in where the force F refers to the total tangential force that the substrate is giving to the water molecules. Here we see the charge profile across the channel for different cases. As it can be seen, for cases 2 to 8, there is an area where the nominal charge is reversed. Therefore, we can determine charge inversion is occurring for these cases. And as well, as we see, as the share of the multivalent counterion increase in the solution, so does the magnitude of the inverted charge depicted by the area in where the nominal charge is reversed. On the other hand, from the result from both diffusivity and the friction coefficient, we can appreciate that there is a decay on the free movement of water molecules, specifically at the interface. Moreover, we wanted to inquire about the dynamic behavior of the system. Therefore, we conducted non-equilibrium molecular dynamic simulations in which we reproduce electroosmotic flow by applying different magnitudes of electric field to the solution. With them, we construct velocity distribution and shear stress profiles across the channel, and we also compute the zeta potential using the concept of stream mobility that is presented up here. Here we can see the velocity distributions for 5 cases with we are submitted to the 3 different magnitudes of electric field. As you can appreciate, for the cases where charge inversion is developed, there is a reverse in the direction of the flow. This can be explained by the drastic change that is occurring on the electrokinetic driving force at the diffuse layer, as it now contains some region where the nominal charge is reversed. Here we see the shear stress profile across the channel. In here we can also see that as charge inversion is being developed in the system, remember that charge inversion is not occurring for case 1 and is increasing, for case 2 to 5. We can see here from the shear stress that there is a decay in the maximum shear stress experienced at the proximity of the wall. This could be explained by the lengthening of the electrical double layer, as it is now containing an extension where the nominal charge, the reversion of the nominal charge, is occurring. Here we see the result from the zeta potential, which goes in agreement with our previous result. This previous information, and acknowledging that there is an enhancement of the viscosity given the electroviscous effect, we can determine that as charge inversion is being developed in the system, it affects its electrokinetic driving force at the diffuse layer, which further modifies its behavior. Furthermore, as we wanted to improve our knowledge about how the bulk and interface region were being affected by this anomaly, we conducted 2 additional types of non-equilibrium molecular dynamic simulations. First, we have Poiseuille-like flow, in which we model pressure gradient by applying an acceleration field to the water molecules. With this, we inquire about the bulk viscosity using this relation that is an approximation of a one-dimensional flow of the Navier-Stokes equation. And also we conducted Couette-like flow simulation, in which we maintain the upper wall fixed and move the lower one with a constant velocity. With these 2 types of N and D, we inquire about the location of the shear plane, and the gel-like or local viscosity, that will be the viscosity at the interface, that could be found with this following boundary condition at the location of the shear plane. From here we see from the velocity distribution of the Poiseuille-like flow There is a decay in the velocity, maximum experience velocity at the center of the channel at the shared multivalent control ions, and as well the charge at the magnitude of inverted charge, increasing the solution. Here from the inside, we can appreciate that if we take the approximation where the location of the shear plane will be, we can see that this location is further from the surface as the charge inversion is being developed in the system. This location of the shear plane could be better appreciated from the simulations of the Couette-like flow. It's right to say that this location of this shear plane was in good agreement with the simulation from the Poiseuille and the Couette-like flow for all cases. Also, this shear plane location does not determine where the solution starts its translation movement, but rather where the velocity gradient drastically changes. Using the previous information, we computed the gel viscosity, the bulk viscosity, and effective viscosity, which is an algorithmic sum between the two of the previous mentioned. The result of this viscosity reveals about the increase of the solid liquid interaction that is occurring as the magnitude of the inverted charge increases in the solution. And finally, I would like to present you my conclusions, which basically states that as charge inversion is being developed in the system, it further modifies its hydrodynamic behavior by a buildup of the solid liquid interactions, changes in the electrokinetic driving force, specifically at the diffuse layer, and modifying the zeta potential. Here I would also like to acknowledge the UCO project and Condensate for funding this research, and thank you very much for your time.